So step one in our path toward a multivariable chain rule is just to go back to think about the single variable chain rule one more time, right? The chain rule is something we learn in single variable calculus when we want to find derivatives of composite functions. A composite function is just what happens when I take one function, we might call it g, and another function which we call f, and we feed the output of g into the input of f. So that what I get is f of g of x, right? F applied to the result of g of x. And so this new function that I get, which sort of goes from the original beginning to the ultimate end, is called the composition, and sometimes it's written f circle g, right? So that's the name that we give to that function that does both of those steps and can sometimes obscure the step that's in the middle. And so in your single variable calculus class, you had to do take a function that was a composition and break it apart into its constituent parts in order to use the chain rule to compute its derivative. And then the chain rule in single variable calculus told us what the derivative of the composition, f circle g, is equal to. So if I want to take the derivative of this composite function, using the derivatives of each of the functions f and g, right? So the function g has a rate of change that quantifies how this output changes as a proportion of changes to this input. And so there's a derivative that exists along this first step that we would call g prime. And that derivative is going to be evaluated at the input that the function is getting. So the rate of change here is g prime of x. I'll say that that's my rate of change, ROC. The second step is we're applying a function f, and that function is going to have a rate of change. Again, as long as f is a differentiable function, it's going to have a rate of change that we would call f prime. But that rate of change is being evaluated at the input that function is receiving. And since this function is receiving the input of g of x, that is also where its rate of change gets evaluated. F prime evaluated at g of x. And once we know the rate of change at each of these steps, the total rate of change from beginning to end is sort of like asking, well, let's suppose that I'm increasing my hours at work by 1 hour per month. So I have 1 extra hour on my schedule every month at work. And I also know that for every additional hour that I work, I get $20 or something like that, because that's my pay rate or whatever. And so if every month I get 1 additional hour and every hour gets $20 additional, then that means that the total number of dollars extra that I'm getting every month is 1 times 20. Right? If I were to get 3 more hours every month, I would get 3 times 20 additional dollars every month, and so on. So the net rate of change from the original input to the ultimate output is just what we get by multiplying these two individual rate of changes along the way. So the derivative of the composite function is the derivative of g, evaluated at x, so the rate of change on this part of the pathway, multiplied by the rate of change of f, evaluated at g of x. And I'm writing these two factors in probably a backwards way to what you usually see them, just because I kind of want to emphasize their connection to what's happening in this diagram here, right? It's the rate of change of my first step multiplied by the rate of change of my second step in the composition. So if that's the single variable chain rule, then the question that we need to try to confront is what happens for functions of more than one variable? So how should we be thinking about what a chain rule should even look like for functions of more than one variable? So I want us to start this work with the preview activity from the relevant section. So this is section 10.5 in our text. And the way that this activity starts us out is by sort of providing us with a context in which a composition of functions of several variables might actually be helpful, might actually be valuable. So the example that they give here is that we have a parameterized curve. And a parameterized curve is a vector-valued function. It takes one input, t, and it produces 2 scalar outputs, or a vector output, x of t, y of t, right? And so that parameterized curve sort of describes maybe the position of a particle or a car or something, right, that's driving, and t might represent a time variable or something. But then we can feed that output, the location of a point along this parameterized curve, we can feed that location into a function of two variables, like this function down here that represents the temperature at any point in the xy plane. And the result of that is going to be a scalar output. So it's like you give me one scalar as an input. I turn that scalar into a vector in the xy plane that tells me my position. And then I have another function that turns that position into a temperature at that position. Right? And so what our diagram for that might look like, if we sort of use the same kind of picture that we did for the single variable chain rule, is that I might have my time variable here that then determines both an x-coordinate and a y-coordinate. And this function is my vector-valued function that we would call r. Right? So it determines an x-coordinate of my location and a y-coordinate of my location. These together form a location. Right? And then each of those, x of t and y of t, we need to feed both of those coordinates into the function that we're calling capital T here that tells me the temperature at any given point on the xy plane. And so what we get here is a composition that we might call T of x of t, y of t. So that's the sense in which the composition, T composed with R, would be a function that is a scalar valued function of a single scalar input, right? Because it just goes from beginning to end here. T composed with R is going to take the time and produce for me, whoops, I didn't write it, the temperature at that point in time on my parametric curve. So the composite function wouldn't even see this sort of vector valued thing that's happening in the middle. It would just be a function of a single variable, little t, and it would produce for us a temperature, capital T. And so our goal in this first preview activity is going to be to reason our way into a principle for how should the derivative, the rate of change of this composite function, which would be how is my temperature changing with respect to time, how should that rate of change depend upon both the rates of change of this parameterization, in other words, my velocity vector at any given point in time, right, the derivative of this r function, and also depend on the rates of change of the temperature with respect to changes in the location, and those would be partial derivatives with respect to x and with respect to y. So if you like, we could sort of list on this diagram what are the rates of change that we might expect to see showing up in here. Well, my velocity vector is going to have kind of this pair of scalar rates of change, x prime of t and y prime of t. And then my temperature function, because it's a function of the variables x and y, it's going to have rates of change given by the partial derivatives, partial of t with respect to x and partial of t with respect to y. And so there's four different types of derivatives that are at the party here. So we have to figure out what combination of those partial derivatives is going to tell us the total rate of change, the net rate of change in the temperature per unit change in the time. So how is the temperature changing as a function of time, and how does it relate to these other partial derivatives along the way? So the first way that we're going to approach this is the explicit way, the explicit pathway. And what that is going to have you do is just actually find a formula for this composite function, t composed with r, as a single variable function of t. Once you write that all out, we just have the kind of function that you could have analyzed in your single variable calculus class. And so you can take the derivative in the ordinary fashion. But then after that, in part B, it's going to be asking you to use the idea of linearization, specifically linearization of the function t of x and y, to reason our way into what a chain rule should look like for this problem. But the first step is just to do that as an explicit problem. So find a formula for the composition of t of x of t, y of t, with the function t being given here and the parameterization r of t being given up here. Find an explicit formula for it and then use that explicit formula to find the derivative. And then we'll move forward from there. Right, so picking up the story, when we do this the explicit way, which by the way is always an option when multivariable chain rule is in play, we can always do what you did here and just find an explicit formula for the composite function that totally obscures the fact that it is a composition at all, and then find its derivative. which is what you did here. And so the question that they want us to sort of think through here is where inside of this composition, or this giant sort of derivative that we wrote down here, where can we find things that look like the derivatives of maybe my original parameterized curve components, so 2 minus t squared and t cubed plus 1. Well, when I look in here, I can see those partial derivatives, or not partial derivatives. I can see those derivatives of my original function popping up as the 2t and as I guess a minus 2t. So I think I might have messed up a minus sign here. So minus 2t. And then the 1/5, and I have a 3t squared over here. And so I can see the derivatives of my first function in my composition. They're just popping out right there, 3t squared. All right, so let me update that just so that it's accurate. So let me zoom in on this just to make sure we're seeing the same thing. Okay, so here, minus 2t is the derivative of the first component of my parameterized curve, my function capital R. And then 3t squared right there is the derivative of my second component. So that's probably not an accident. Let me just write the next line here and replace those with their more meaningful versions. But then another thing that I notice happening in this example, so this minus 2t here was x prime of t, and the 3t squared was actually y prime of t. Put an update on that. Because I can also see the original functions x of t and y of t, so the actual original components of this parameterization, are also kind of showing their faces in this expression. 2 minus t squared that I'm seeing right here, that actually is x of t. And t cubed plus 1, that actually is y of t. So we can keep going. We do even sort of one step better here by replacing 2 minus t squared with just plain x of t. Maybe I'll even suppress the of t notation just to make the resulting thing a little bit easier on the eyes. So if I update this, I'm replacing 2 minus t squared with x. I'm replacing t cubed plus 1 with y, because that's what they meant in my original parameterization, right? Okay. And now if I look at what I have here, I have negative a half times 2x. And what is negative a half times 2x? That's actually the x partial derivative of my t function, right? Because with respect to x, everything else is a constant except for this middle term, and its partial derivative is minus a half times 2x. So that minus a half times 2x is nothing more than the partial derivative of capital T with respect to x. Similarly, minus a fifth times 2y is exactly the y partial derivative of my capital T function. And so what we have kind of talked, what we can talk ourselves into on this example. Sorry, I gotta open this sidebar one more time here. Is that this derivative was really nothing more than a sum of products of other derivatives. Oh boy, I'm screwing everything up here. So when we reinterpret, as much as we can reinterpret here, what we end up getting is the partial derivative of t with respect to x times the derivative of x with respect to t, added to the partial derivative of t with respect to y, multiplied by the derivative of y with respect to t. So what's really happening here? What's really happening is that there are sort of two different mechanisms, two different ways, two different paths through which a change in our original variable can affect a change in our ultimate output variable, right? And each of those different paths from beginning to end, each of those different paths from small t to capital T, is going to be associated with its own rate of change. And its own rate of change can be computed just using the single variable chain rule. So it's like if I just think about how little t affects capital T through the x quantity, then only the x partial derivative of capital T is going to matter, and only the derivative of x with respect to t is going to matter. And along that pathway, those rates of change are going to multiply together to give me the net rate of change according to the single variable chain rule. So when I want to find the derivative of capital T with respect to little t from a diagram, so I like to call this either a network diagram, or in the textbook they call it a tree diagram, and they draw it just a little bit differently. I like to think of it as just find what are all of the paths from my input variable to my output variable that exist in this diagram. And for each one of those paths, like this one, we will write out a rate of change using the single variable version of the chain rule, except that in the cases where we have a function of several variables, we just have to remember that those derivatives are partial derivatives instead of ordinary derivatives. So this capital T has a partial derivative with respect to x that quantifies this rate of change, and then x of t has an ordinary derivative with respect to t that quantifies this rate of change. I multiply those together, and what I get is the contribution of this pathway to the total net rate of change of capital T with respect to little t. And then if there are other pathways, I quantify their rates of change as well. So that contribution which t makes to capital T mediated through the variable y in the middle is going to be associated with the rate of change, which is the product of the partial derivative of t with respect to y times the derivative of y with respect to t. And all of those contributions are going to add together to give me the total rate of change. So this is what the chain rule ends up looking like in a multivariable context, is that when there are multiple input variables and maybe multiple different ways that they can impact output variables, we just have to account for all of the different pathways, all the different routes from the input that we're interested in to the output that we're interested in, and use the ordinary chain rule to compute the rate of change along each of those paths, and then just add all of those results together. And this version of the chain rule is sometimes, I would say maybe at least 50-50. It's probably, in most cases, a little bit simpler to use than just doing the explicit work that you did in part A, to just find a formula for the composite and then just take an ordinary derivative. Having the chain rule, being able to do the chain rule in a fashion like this one is a slightly more elegant solution, usually involves a little bit less work. So let's do one example of sort of putting this strategy for the chain rule into practice. So I want to take maybe not a ton of time because we're starting to get close to the end of our hour, maybe 5 or 10 minutes, and I'll pick one of the activities from further down on our sheet to do. And then we'll come back together, and I want to talk a little bit about the more sophisticated way to view what the multidimensional chain rule is telling us.